Hello everyone, welcome back to the MOOCs course on Advanced Analytical Techniques. Today we'll discuss about the historical background of analytical spectroscopy. The analytical spectroscopy was mainly originated from the work of G.R. Kirchhoff, who is a German scientist. He, in the year 1859, reported that each and every pure substance has its own characteristic spectrum. And this discovery has become the basis of analytical spectroscopy. However, he was not the first to work on spectroscopy, or I should say the spectrum. Before Dr. G.R. Kirchhoff, there is a scientist, British scientist William Wollaston. He worked on the spectrum of sun in the year 1814. And then Joseph Fraunhofer, based on the work of William Wollaston in 1814, he further worked on the spectrum of sun and reported that sun spectrum is basically a type of absorption spectrum. Although sun emits an spectrum, continuous spectrum of bright lines, which is a continuum of bright light. However, at some distances, some gases with lower temperature, or I should say the cooler gases, they absorb certain wavelengths, resulting into black lines in the sun's spectrum. And therefore, sun spectrum is considered as an absorption spectrum. The 19th century, means the year of 1859, 1860. Basically, the 19th century was mainly devoted to the spectrum of sun as well as hydrogen. And in the 20th century, the various spectroscopic techniques have been developed gradually. For example, there were certain scientists who were working on the characteristic spectrums, after the reports of G.R. Kirchhoff that each and every pure substance has its own characteristic spectrum. But at that time, the main difficulty that they were facing was the availability of pure sample. That was quite difficult to get, and therefore Kirchhoff worked very hard to obtain the pure sample so that their characteristic spectrums can be obtained, can be generated. Then in the year 1930, a chemist from Denmark, a Danish chemist, Niels Bohr, you must be aware, he is the scientist who put forward the very famous atomic model in the year 1930, where he reported that the electrons orbits around the nucleus in the circular energy levels at very high speed, so that they cannot fall, and those energy levels, they are being placed and they are moving in those energy levels only. So he gave that very famous Niels Bohr atomic model in the year 1930. So he theorized, he also worked on hydrogen spectrum, and he theorized, he calculated the energy levels of hydrogen spectrum, and then he theorized that each and every level has a quantized value of energy, and if we provide that particular value of energy, there will be excitation of electrons. Now, spectroscopy is broadly divided into two categories. One is called the absorption spectroscopy, the other is called the emission spectroscopy. Then various other spectroscopic techniques are the subclasses of these techniques. Either they belong to absorption spectroscopy or emission spectroscopy. But spectroscopy broadly is divided into these two categories, absorption and emission. Now, what is the basic difference between these two? When a sample is irradiated with a certain region of electromagnetic radiation, for example, we are giving ultraviolet light, which belongs to a particular region of an electromagnetic spectrum. I explained in the previous class about the electromagnetic spectrum and the various wavelengths level and the corresponding frequencies. So I told you that it starts from gamma radiation, then we have X-ray, ultraviolet, then IR, microwave, and then finally we have radio waves, very long wavelength. So on the basis of wavelengths, we can select any of the region of electromagnetic spectrum, and if that region is basically irradiated on a sample. For example, this is a sample which contains an atom. There is a, for example, there is a sample which contains an atom, and this atom is excited, is irradiated with a electromagnetic radiation of certain wavelength. Then what will happen? Some of the wavelength are being absorbed because of the interaction of the various atoms or groups present in that sample, and those wavelength that are being absorbed by the sample, they will result in a dark lines on a bright background. For example, if we are giving visible radiation to a sample, then most of the radiation will go unaffected. Those radiations will form a continuous bright spectrum, while some of the radiation, some of the specific wavelengths are being absorbed by the atoms or the groups present in that sample, and those wavelengths will be missing in the main spectrum, and they will appear like dark lines on a bright background. So this is called as an absorption spectrum, and the same and a similar spectrum is produced by sun, which is again a bright continuous spectrum having some dark lines, and those dark lines, as I said before, are formed by the absorption of certain wavelength by comparatively cooler gases. Now coming to the emission spectrum. Emission spectrum is on the other hand generated by emission of light. Now there is a question, from where the atom will get energy to emit light? Now in this case, we do not require a light source, as we need a light source in case of absorption spectrum. As I said, that when we irradiate a sample with certain wavelength radiation, this is needed for an absorption spectrum, but not for an emission spectrum. For an emission spectrum, we need energy, but we do not need light. We do not meet out that energy requirement by giving incident radiation. So we do not, although we need energy source, but that energy source is not the light radiation. Therefore, in emission spectroscopy, always remember that a light source is not needed. What we need is an energy source. That energy source is basically heat, which is provided either by a flame, by lighting a flame and heating the sample, or by an electric discharge for heating the sample. We have to heat the sample, we have to provide thermal energy to the sample either by direct flame or by an electric discharge or even by a plasma. Then based on the energy gained by the atom, its electrons are promoted to the higher level. When those electrons comes back from the excited level to the ground level, they emit light of certain characteristic wavelengths. So there is no light before this excitation, and therefore an emission spectrum is basically a dark spectrum. Emission spectrum is a dark spectrum where we have certain bright lines due to the emission of light by these excited atoms. I'll explain you and show you how an absorption spectrum and an emission spectrum appears in the next few slides. So this is the spectrum. This is for emission spectrum. This is for absorption spectrum. As I said, that an absorption spectrum, since we are using a light source, since this light source is used, we get a bright background or a continuum of bright color. Then these light radiations are interacted with some sample. It may be a gaseous, then these light radiation then interacted with a sample, maybe a gaseous sample or a liquid sample. Some of the radiations will be absorbed. Those radiations which are being absorbed by the sample, they appear as dark spots. So these 4, 5, 6 dark lines in this spectrum, they basically corresponds to the wavelengths that are missing, and these wavelengths are missing because they are being absorbed by our sample. In contrast to the absorption spectrum, our emission spectrum, as I said, since we are not using any light source, we have a continuous dark background. Then the excited sample, for example, in this figure, we have shown hard gases. It may also be possible that we have a liquid sample and we heat that liquid sample. So atoms will get energy, the electrons are excited, just like in a hard gas when electrons are excited. And these electrons are promoted to the next level. It may be even level, or they may be promoted to E2 level. So when they return back, they emit light radiations. And these light radiations are being available, and these light radiations are being shown on this dark background. And these lights are, and these lines corresponds to the sample being present, and these lines corresponds to the atoms or groups being present in this excited sample. This is again a figure showing you the two types of spectrum and also a continuous spectrum, just to give you more uh, just to give you a clear idea about what is a continuous spectrum and what are emission and absorption spectrum. And what are emission and absorption spectra? Remember, spectra is a plural word for more than one, and then if we have a single spectrum, we call it as spectrum. So this represents a continuous spectrum. This basically is emitted by sun, but due to some gases which absorb certain radiation, there are some dark lines, and therefore the spectrum of sun is considered as an absorption spectrum. Then we have an emission spectrum. Again, as I said, emission spectrum is a dark spectrum with few bright lines that corresponds to the sample under investigation, and this shows the continuous spectrum. So absorption spectrum is basically a bright spectrum with some lines, color lines missing, while emission spectrum is basically a dark spectrum with only few color lines, and therefore an absorption spectrum is considered as a continuous spectrum, while emission spectrum is considered as a discontinuous spectrum. Can also be known as it is also known as line spectrum. So emission spectrum is called as a discontinuous spectrum or a line spectrum, while absorption, we can see a bright background with few dark lines only, so it is called as a continuous spectrum. So let us study the absorption is the let us study the principle of absorption spectroscopy. So absorption spectroscopy, what will happen? For example, we have a sample and we are giving light to the sample. The atoms or the molecules present in this sample, they interact with light. They absorb some of the radiation, while the remaining radiations will be transmitted and they fall on the detector. This is our detector, for example. I'll discuss more about detector in the later slides of this unit. So when these transmitted light falls, we get a bright spectrum, and then we have those missing lines. So atoms and molecules, what happens in absorption spectroscopy? The atoms and molecules that are present in the sample, they absorb photons. I explained in the previous class that the electromagnetic radiation is nothing but when a subatomic particle is excited in electric field, it creates an oscillating electric and magnetic field that are perpendicular to each other, and they carry energy in the form of small packets. Those packets are called as photons. When these photons fall on a sample, for example, we have a sample in this container. When these photons fall on this, from here we are having photons coming, then the atoms and molecule present in the sample, they absorb those photons, and when they absorb, they got excited, and when they get excited, they transfer their energy to the electron, and the outermost electron is promoted from energy level 0, which is called as the ground state, to first excited state or maybe the second excited state. This is mainly the concept of absorption spectroscopy. And each and every sample has its own characteristic wavelength. This is this is what has been reported by Kirchhoff in 1859, that each and every pure sample has its own characteristic spectrum. So they have a characteristic wavelength. They absorb a light of characteristic wavelength. So each and every sample has a characteristic wavelength. Now, the amount of light absorbed is governed by a famous law called as Beer-Lambert's law. And this Beer-Lambert's law states that the absorption of light, or the amount of light which is absorbed, is equal to epsilon C and L. Basically, this absorption, the amount of light absorbed, is proportional to the C, the concentration of the sample. This amount of light absorbed is also proportional to the L. L is called as the path length. For example, if this is our container, so the breadth of this container, this is actually the path length through which this light will pass. And because in this region only the light will interact with the sample, so this path length has an important role. For example, if we have a sample tube which is having long path, so here in this sample we have, in this path we have different types of atoms and molecules, so the light radiations will have more time to interact with them, so it will ultimately results in higher level of absorption. While if we have a sample tube which is very thin, the level of absorption would be very small, and therefore absorption is directly proportional to the length, path length. It is also proportional to the concentration. The higher the concentration of the sample, higher will be the number of atoms and molecules present, and if higher be the number of molecules and atoms present, there will be more interaction, resulting into more absorption. So combining these two, we have A is proportional to C into L, and when we remove this proportionality sign, we have A is equal to epsilon C into L, where A is the absorbance or the amount of light absorbed, C is the concentration, L is the path length, and C is the molar absorptivity, which is characteristic value for a particular sample.